Hi all and welcome to this presentation. I'm gonna be summarizing Professor Stevens Boy's lectures on model predictive control, and hopefully I will keep it under 10 minutes, depends on how deep we dive into each topic. So this is the course content. We first start with the linear convex optimal control part, then I will move to the finite horizon approximation, then to the model predictive control part with the fast MPC implementations, and I'll end up with an example on supply chain management. In the linear convex optimal control problem, we want to minimize the cost function j, which is summation from 0 to infinity of a function that depends on both x of t and u of t, where x of t is our state vector and u of t is our control input. We are imposing that our control, some constraints on our objective function. U of t should be, our control input should be feasible, and thus we limit it to our script u set, and x of t should be also achievable, and thus should be in our script x set. Our dynamics are also linear, x of t plus 1 is equal to x of t plus b of t, and our initial condition on x of 0 is equal to z. Two options for the optimization problem: either we consider u of t and x of t to be our optimization variables, or we only consider u of t to be our optimization variable. This really depends on the problem that you are dealing with, and it has its advantages and disadvantages in some cases. In greedy control, we want to minimize the cost function that we previously defined over all control inputs that are in our script u set. Thus we choose our u of t to be the argument of the function L of x of t comma w for all possible w's in our script u set, and we are also imposing that our future state vector x of t plus 1 should be also in our script x set. This type of control is not optimal since if norm of a is squared, since norm of a is small, x of t plus 1 does not depend much on x of t, and we call this a feigning memory problem, which has its disadvantages because the control, the previous state does not really affect the future state, which is really bad in some cases. The solution via dynamic programming is as follows. V of z is the infimum of the previously defined function, but now we are choosing it over all possible state vectors and control inputs, and we are also adding cost that is v of a of z plus bw, which is the cost of moving a step ahead in the state vector, which if you want to think about it, is the cost of moving to the next step. Now v of z is called the value function or the Bellman function. It is a convex function, and the optimal control input is given by u star of t, which is equal to a function of x of t, which is the argument of the L of x of t comma w plus v of ax plus bw. In LQR control, we choose L of x of t comma u of b to be quadratic in x and u, where q and r are matrices such that q is positive semi-definite and r is positive definite. Our script u set should be in Rm, and our script x set should be in Rm. Now q and r can be seen as costs for each element in the state vector and control input vector. So for example, if we have a state vector of 3, we can choose for our first two elements to be in our diagonal matrix to be 10, 10, and for example the third one we can choose 1, and so we can play around with it depending on the problem that we want to solve. Now the value function is obtained as v of z is equal to z transpose pz, where p is positive semi-definite and is obtained by solving the algebraic Riccati equation. Now the optimal control input is found to be u star of t is equal to kx of t, where k is our feedback gain and is equal to minus r plus b transpose pb inverse b transpose ba. Now here we can notice that our control input only contains a feedback term and does not have a feed-forward term, which can be really bad in some cases. But here we can notice that P is the summation of Q plus a Schur complement of a matrix that we'll see in the next slide. Here we can see that the algebraic Riccati equations is defined as A transpose P plus PA minus PB R inverse B transpose P plus Q, and solving for P we obtain P is equal to Q plus S, where S is the Schur complement of this matrix, and this really gives a new view on a new look on the algebraic Riccati equation solution. In finite horizon approximation, we don't sum over infinity, we sum over a specific control horizon t, where t is chosen depending on the problem. For example, in motion planning algorithms for a robot, for a wheeled robot, for example, we can choose our control horizon to be equal to 10, and thus we are specifying that we want to plan 10 steps ahead at each time that we move. And we are also constraining our problem where u of t is in our script u set, and x of t is in our script x set. These are the same constraints as before. Our problem is also linear, it has a linear dynamic model, and we are imposing that our initial state is equal to z, and our final state, which is our final control horizon step, it should be equal to 0, but this really depends on the problem and you can play around with it. And this type of control is limited because the solution for u of t is suboptimal, and this is because we are working in a finite dimensional subspace. In fact, we are choosing u of t is equal to 0 for t, small t larger than or equal to big T. So once we plan for our 10 steps ahead, for example, we set our remainder control input to be equal to 0. In LQR here, we solve for this problem, and we choose x of t to be in r cubed, u of t to be in r squared, and the a and b are randomly chosen. Script x set is defined as follows, and the script u set is also defined as follows. And this really depends on the problem that you are dealing with. So these are randomly chosen, and the stage cost is defined as the 2 norm of v squared plus the 2 norm of w squared. And also this is randomly chosen here, the initial condition on x. And you can see for a control horizon of t is equal to 10, we can achieve really good results compared to the optimal solution. But for big T larger than or less than or equal to 10, we cannot, less than 10, we cannot, the problem is unfeasible and we can't achieve our optimal cost. In RHC, in model predictive control, this it has its definition and general applications. First of all, it's called also receding horizon control, finite look ahead control, dynamic linear programming. These early implementations included also chemical processes, supply chain management, and revenue management. Now, these limitations on implementations were due to the fact that computers back then were really slow, so they couldn't solve quadratic equations very fast, and they resorted to PIDs instead of MPCs. Now, in model predictive control, we want to minimize the silly cost function, but from tau is equal to small t to big T plus small t. This means that we are planning a specific control horizon which is equal to big T, which is equal to, for example, 10. And here we are planning at each time step in time, at each time step 10 steps ahead. For example, in robot motion planning algorithm, we can plan for 10 initially, move one step further in time, then replan for 10 steps forward. So actually relaxing the constraints if you want to think about it. We are not only considering 9 steps once we move one, we are also replanning for 10. And the same constraints apply for u of t and x of t. And here x of tau plus 1 is also linear in x and u. And our final condition on our state vector should be equal to 0. And we can see here the results are pretty good for big T is equal to 10. And we can notice here in MPC and finite horizon approximations, the finite horizon approximation really gets close to, it really works well for T is equal to 10, but isn't feasible for T less than or equal to 10, less than 10. And in MPC, it starts off very well. Actually, it's very close to the optimal control at first. Some variations on MPC include that we can choose our final state to be equal to an estimate of our cost function, which is the same as we did in the Bellman function equation. We can also plan for k steps in time. So, for example, if we are planning for a control horizon of 10 steps ahead, we can move for 5 instead of planning for 10 and moving for 1. We can plan for 10 and move for 5, then replan for 10. So this is like lowering the frequency of our control algorithm. Now we can convert also our hard constraints to validation penalties to avoid planning problem and feasibility. This means that in cases where our problem is not feasible, instead of having nans as answers, we can actually allow them and have penalties on these nans. The problem structure of the MPC is really interesting. Our hashing block is block diagonal, and the equality constraint matrix is block banded. This means that the control input and the x of t, which is our state vector, are highly correlated, and in fact this is due to the choice of our dynamic linear model. So x of t plus 1 depends on x of t and u of t, and this is why it's block banded. Now this means also that we can solve the problem really fast, and because of its structure, and we can solve it in the orders of t times n plus m cubed. Here are the solutions by coding in C and not in MATLAB. So we can see for a control variable, for a control problem, which an optimization problem of big size, where the number of variables is 1000 and the constraints are 3000, we can solve the problem using fast MPC in 23.4 milliseconds compared to GPT-3 in CVX, which is 3.4 seconds. In supply chain management, this is an interesting example where we can see the really good use of MPC. For example, I'm gonna be taking the water treatment facility to be more precise on the terminology of these equations. First of all, let's assume we have n nodes for storing goods, which means that we have n tanks in our water treatment facility. The m links between nodes are pipes, so we have m pipes relating each tank, for example, with another tank or the exterior. X of I of t is the amount of commodity at node I, which can be denoted as the amount of water in tank I, which is in n. And the U of j of t is the same but for pipes, so the amount of water in pipes. Now we also have this matrix A, where it denotes the incoming and outgoing node incidence flow direction in each pipe. So if it's going from A1 to 2, so it's between tanks 1 and 2, we can have it equal to 1, and if from 2 to 1 we can also have it 1, but otherwise it's 0. And the dynamics are also linear. In fact, the amount of water in the tank at the future time step is equal to the amount of water in the tank now, plus the amount of water flowing in minus the amount of water flowing out. And we want to minimize this objective function, which is the summation from t is equal to 0 to infinity of s of u of t plus w of x of t, where s is our shipping cost and w is our storage cost. We are also imposing constraints on xi of t and uj of t to be limited to x max and u max. And here the third condition is that a out times u of t is less than or equal to x of t. So here this means that the amount of water flowing out of a tank should not be greater than the amount of water in the tank in the previous step. Okay, here we chose n is equal to 5 and m is equal to 1, and these are also randomly chosen. And for the cost function, it is for the storage cost function, we take it as to be quadratic in x, and for the shipping cost, we take it to be the amount of water flowing in minus the amount of water flowing out. And we can see here for a control horizon of 5, we can achieve very good results. Here we saw that the cost function of MPC is equal to 69.5, which is very close to the optimal solution, which is 68.2. We have also variations on MPC. We can vary the time, costs, the dynamics and the constraints. We can also couple the state and input constraints. We can add a slew rate constraint, which means that the control input here, the control input in the future time step is really dependent on the previous time step, which smoothens out the control input signal. And this also will make our algorithm converge to the solution very fast because of the block banded matrix on the constraints. And we also have an important part, which is the stochastic control. Here I'm gonna just discuss a brief introduction to stochastic MPC. We have our dynamic system is also linear, but here we are adding a new term, which is omega of t, which is a disturbance. But now x of 0, which is our initial state, and all the disturbances are random variables, and we want to minimize this objective function, which is an expected value of the summation of a function that depends summation from 0 to our control horizon of a function that depends on x of t and u of t plus a new term, where this new term is the same as we have previously seen in the Bellman equation. It's the cost of moving to the final step in our control horizon. And now we choose we want to choose our okay, so in MPC we were choosing our control input, but now we are choosing the control policy behind choosing our control input. So this is the main difference. Now we choose the phi's from 0 to t, big T minus 1 instead of choosing u of t, and these are the new problem variables. Thank you. This is the references that I used, and I highly recommend watching Professor Stephen Zaboy's lecture on YouTube to get a better insight on what I just explained. But hopefully the summary was entertaining and complete. Thank you for watching.